Okay, so last time we were talking about vector fields. You can just turn it in like that. So keep in mind what a vector field is. We have this picture. The idea is that we would like to be able to express for any given point the idea that we can associate to that point some vector representing, of course, keep in mind vectors represent a direction and a magnitude. So we talked about, this is the two-dimensional version of that. Here's what it might look like in 3 dimensions. Of course, then the vectors are also 3-dimensional vectors. And we made the observation that you can think of these as functions. So specifically, whatever point you're talking about, whatever point, given a point, there is an associated vector, which of course is an element of Rn. So you can think of this, an input point gives an output vector. An input element of Rn gives an output element of Rn. You can think of a vector field as being a function from Rn to Rn. Okay. So that's just, how to write it algebraically. And of course we're going to be using that a lot algebraically. Here's an example. The input point, the location x comma y, the associated output vector given by the formula, and such as that. Okay. All right. So some examples we didn't quite get to last time. And let me just remind you while we're here, the picture that we draw here, it's not a graph. And y'all remember I'm real big on this idea of, keeping a careful eye on what is this picture and how is it constructed. Specifically, how is it constructed from a given function. And remember, it's a very, very big deal that a graph is constructed by a completely different procedure from how a level set is constructed, which is a completely different procedure from how an image is constructed. In other words, if you're talking about like a parametric curve, what's the associated curve is the image of the parameterization. Those are all completely different processes that associate algebra to geometry, right? And so, no surprise, there are completely different interpretations. How does the calculus of the corresponding function relate to the geometry of the corresponding picture? Totally different, right? Calculus of level sets, you might say, totally different from the calculus of graphs. Well, likewise, yet another example here. These pictures that we're drawing, right? These are not graphs, and they are not level sets. It's a completely different kind of picture. So don't take graph interpretations of calculus and try to make sense out of them on pictures of vector fields. It just doesn't make any sense. Okay. All right. Nevertheless, so here's a couple of examples. Let's look at this one where the vector field formula is 2, 1. What that says then, at every point x, y, wherever you might be looking, the associated field vector is, 2, 1. 2, 1, always the same vector. So from every point in this two-dimensional space, x, y, we get an associated vector. It's always the same direction, always the same magnitude. And that's a picture that's approximately like that. Okay. Another example here. Let's look at this formula. F of x, y is x, y. What that says is at any given associated point, I'm just going to draw a couple of them here. Any particular point, the associated field vector, here's the formula. It's x, y. What does that mean? That means that the field vector is the same vector as the position vector for the point. Here's the position vector for those points, or position vectors. How we associate points to vectors are, tail at the origin. So the field vector is the same as the position vector, means that these field vectors are kind of like this. Right, and notice that position vector is the exact same as that field vector. Same direction, same magnitude. We draw them differently. When we think of a position vector, we put the tail at the origin. When we think of a field vector, we put the tail at the associated point. So their arrows are drawn in different places, but they're the same vector. Right? So this is a reference to a way old concept back in chapter 12. Likewise, the position vector is the same vector as the field vector. Okay. Here's one more example. And by the way, some bad news. It's not always the case that you can look at a formula, however complicated, of a vector field and just draw a picture of it. It can be really hard. Right? So this is going to be a short list of convenient examples. So here's one. How would I understand this vector field? How would I draw a picture of this? F of xy is negative y comma x. So first observation to make is that the position vector of the input point and the field vector that you associate to that point, those two vectors have the same magnitude. They're not the same vector. They have the same magnitude. Right? Furthermore, the field vector is always orthogonal to the position vector. Right? So they have the same magnitude, perpendicular direction, and that leads to a picture that looks something like this. So for example, you take a point like, let's take that point. There's a position vector for this point that we're looking at. And the field vector, the field vector has the same magnitude as that, but points perpendicularly. And so I'm going to say there it is. Notice that's perpendicular and with the same magnitude. Now you may wonder, how did I know it wasn't this? Right? And fair question. And plug in. Right? So if you plug in, x comma y equals 1 comma 0, for example, you notice your field vector becomes 0 comma 1, which is up. Okay. All right. So analogous argument gives all of these different field vectors. And not hard to persuade yourself after, you only have to draw so many of these until you kind of notice the pattern. This is a vector field that's sort of, I'm going to loosely say, kind of swirling counterclockwise around the origin. Something like that. Okay. All right. Again, this is a short, incomplete list of a few examples of where you can look at the formula and make sense of what the vector field looks like. Again, it's not always that easy. Sometimes you can go the other way and you can look at a picture and sort of reverse engineer and figure out what the formula is, or at least a plausible candidate for what the formula is. Okay. All right. There's some examples of that in the homework exercises. Here's another example. This, by the way, is a really important example. This example is really important for reasons that we are not ready to see yet. There's going to be a bunch of discussion that predates that, but next week we're going to start seeing examples of why this is a pretty cool special case of a vector field. And then over the next several weeks we'll see more examples, more sort of reasons why this is a really important example. Yeah, anyway. For now, all I can say is, let me be perfectly obvious with the foreshadowing. This is going to be important. Okay, so here's the observation, and that is if you have a Chapter 13 style real valued function on Rn, real valued means the output is just a single real number. You can take the gradient, and keep in mind how gradients work. A gradient is an associated vector, so then given a point in the domain of this original function f, by taking the gradient, you get an associated output vector. Well, in fact, then, notice exactly what a vector field is algebraically. We didn't think of it that way when we were in Chapter 13. In Chapter 13, we focused on a single point. Okay, we're at this point. Bob is here, right? And at that point, we want to know certain things. We want to compute certain rates or whatever. I don't really care what's going on at these points over there, right? We're focusing very sort of myopically on just one point at a time. So now I'm just saying, let's just open it up and observe that, given any input point, when you write down the formula for the gradient, that is an output associated vector, which can be interpreted as a vector field. And so we will call this the gradient field now. It's just the same gradient that we talked about before. So here is an explicit example, and I'm going to zoom out so it'll all fit. Close. So looking at this function, there's our real valued, notice, single output value. So a real valued Chapter 13 style function on R2. Remember the formula for the gradient? A couple of quick partial derivatives. Now I can draw the graph of this function. There's the graph of that function. Right, old news. Remember the graph is this construction where you set the output values equal to a z, a new variable, in this case z, and then you write down z equals x squared plus y squared, and then you look at the solution set. So there it is. I can also take this now, interpret it as a vector field, and represent that, as a vector field. And so keep in mind, we have rules for how to do this. And this is this vector field is not unlike a vector field we saw on the last page. Specifically, notice the output field vector, 2x, 2y, is just a multiple, scalar multiple, 2 times the position input vector, xy. All right. Okay, so how is it that this how does this dovetail track with? Give me a second. With what we saw back in chapter 13. Well, let's put these pictures together. Here's that graph. Right. Keep in mind when you draw the graph down here is that's the domain, and if inside of that domain you draw the gradient field, right, like that, notice we get a familiar concept. The way we interpreted gradients back in chapter 13 was that at any given point, the gradient points in the direction of fastest increase, or alternate interpretation. If you're looking at a graph, the gradient points in the direction of steepest ascent, where the gradient points uphill. And notice that's exactly what's happening in this picture. You look at the graph, then at a given point down here in the domain, above which, let's say, is a point there on the graph, the gradient vector points in the direction that defines sort of uphill, if you will, on the graph. Now, again, reminder, in chapter 13 we were thinking of this sort of just one point at a time, but now notice, thinking of it as a vector field, this works everywhere. I mean, so this gradient field, that is, at this point, looking at the associated point on that graph, pointing uphill, right, etc., anywhere you might want to be in that domain. Okay, you had a question, I'm sorry.
I just wanted to make sure I was interpreting that right. So you're saying that like a vector field can be like represented by a gradient? Well,
let's say it the other way around. If you have a gradient, you can interpret that as a vector field. And this is a special case. So it is unfortunately not true to say that every vector field is a gradient. That's not, tragically, as it turns out. You'll see why I find that funny when we get into some later discussions. But it's a very unfortunate fact that not all vector fields are gradients. But every gradient can be interpreted as a vector field. Yeah. Right. Great question. Thank you. Okay. So that's one example. Now, one thing you might be thinking to yourself is, okay, we've got a weird little mathematical game here. You're creating mathematical objects, and we're playing mathematical games with them. But what does this have to do with the physical world? Like, we live in the physical world. A lot of y'all are engineers. You're going to be tinkering in the physical world. How does this relate to the physical world? Well, a lot, as is the answer. Here's my first example, and that is what I like to call force fields. In the sense that we're talking about vector fields, where the associated vector represents forces. Don't mean this in the sci-fi, force field protect you from ray guns kind of sense, right? But force fields can be a great tool in representing physical things. For example, y'all have heard the term gravitational field. All right, well, this is an example of a vector field representing forces. Gravitational fields are force fields as follows. Let's think about, some particular point. By the way, here, let's draw, right here is where the mass is. Let's say at that point, you have a mass. Maybe it's planet Earth. Whatever. Right? In fact, let me zoom in for drawing purposes. If that's Earth, right, then you can talk about, well, if I were here, if I were at that point, I can talk about, well, how much gravity, what sort of gravitational force do I experience at that location? Well, at that location, gravity is going to point in a certain direction, namely toward the mass, toward the Earth, right? And with a certain magnitude, and y'all remember the formula for gravity is inverse square, right? Y'all remember high school physics or physical science, whatever they call it. So the force of gravity is inversely proportional to the square of the distance. So you get a magnitude and a direction, namely a vector that represents that force. While on the other hand, if you are a little further away, it remains that the gravitational force is toward the mass, but now further away, less magnitude. The punchline, though, is to every location, we have an associated vector that is a vector field. Right, so vector fields are the perfect mathematical construction for representing gravitational forces as a whole, as opposed to thinking about gravitational force as something that's experienced, sort of one point at a time. Okay. All right. Now, how do we write that mathematically? Here's the formula. Now, this looks wrong on its face. You see this cube in the denominator, and it's very tempting to say, oh, no, that looks inverse cube. That's not really inverse square. This used to bug me when I first saw things written this way. Let me show you why this is, in fact, inverse square, to be honest. Rewrite this just a little bit. Negative G M. Well, let me write it like this. And then I'm going to say 1 over magnitude of x squared, and then times x over the magnitude of x. And the point here, having written it this way, that is a unit vector simply representing the direction. Okay, well, I guess, with the minus sign, that's representing the direction that the gravitational field is pointing, and it's a unit vector. So that as a unit vector, that does not contribute to the magnitude. Said differently, one of the factors of magnitude x here really is just part of how we describe how we use the x vector to describe a unit vector direction. So, in terms of how the magnitude, here's the magnitude formula. How does the magnitude depend on distance from the origin? Anyway, how does the magnitude depend on the magnitude of x? Well, inverse square. Everybody on board? Okay. All right. Okay. By the way, electric fields. Now, a lot of y'all might not have had a course yet in E&M, right? If you've had Physics 152, 162, either of those, then good. If you haven't, you might not have seen electric fields, but an electric field is really kind of a similar situation. If you have not a mass, but a charged particle at a point, then it is the case that at a nearby point, there is an associated electric force between these two particles, and that electric force is going to be in a direction that's along this line. I missed along that line, close enough, along that line there. And with magnitude, that, as it turns out, also inverse square. So algebraically, electric fields actually look a lot like gravitational fields, which is a very convenient fact to keep in mind, as we'll do some later calculations related to that. But of course, they're different physically, right? Gravitational fields are about masses. Electric fields are about charges. Not the same thing. Right? But mathematically, it is really similar. Okay, so hopefully it's no surprise to y'all that these are of great importance in understanding physics and are of great importance in understanding engineering. Electric fields, gravitational fields, kind of a big deal. And vector fields are, again, the perfect mathematical object for describing them. Okay, here's another one, also very important. How do we represent flows of fluids, and I'm going to call these flow fields. So vector fields whose purpose is to represent the flow of a certain kind of a fluid. Well, there are lots of ways, there are lots of situations in the physical world where there are fluids flowing around. In this room, the air is flowing, right? I hear the air conditioning run somewhere, right? And I'm talking, that's blowing a certain amount of air, and y'all are inhaling and exhaling. So there's not much, but there's a certain amount of airflow in this room. And so, for example, at any given point, any given spot, like right here, this point right there, at that location, the air is blowing, let's say, in a certain direction and with a certain speed. Namely, there's a vector representing the velocity of the airflow at any given point. So for every point, there's an associated vector. That's a vector field. Okay. There's lots of fluids flowing that are not terribly different mathematically. How does water flow in the ocean, let's say, or in an aquarium? How is pollution flowing through the atmosphere or through a river or some sort of a other fluid? Likewise, contaminants in some sort of a system, components of the atmosphere, right? What makes up the atmosphere? It's not uniform. It's not this, exactly the same proportions everywhere in the throughout the atmosphere. In R2, well, now this is not a perfect example, but how animals migrate. Animals aren't a fluid exactly, but they're kind of like a fluid if you really think about it. In other words, as seen from really, really, really high up, there's kind of a, if you see a great big herd or a great big flock of birds, there's thousands, hundreds of thousands of birds all kind of flowing. I mean, yeah, they're individual birds, but if you're sufficiently far away, it looks like a lumpy fluid of birds. Kind of, right? By the way, let me remind you, water that you think of as a fluid, it's actually a bunch of little molecules. There's something discrete about water. And yet we're very comfortable thinking of that as a fluid. So likewise, you can think of, flock of birds or, herd of wildebeests or whatever as a kind of a fluid on the surface of the earth. How water flows on the surface of the earth, how pollen moves at different seasons, and this kind of thing can be thought of as a fluid flow. So now this is all of these examples are a little different, but they're all kind of the same in the sense of here. If we were to write these with vector fields, those vector fields are representing flows of fluids. That is pretty darn different from these. Right, gravitational fields, electric fields. Here, the field's not representing a flow of a fluid. Here, well, not really. The field is representing forces. This is two very different physical categories of very natural, very important physical things that just both happen to be represented, as it turns out, by the exact same mathematical construction, vector field. Okay. All right. Now I want to point out this is a very unfortunate. Whoops! I hit the wrong button. Very unfortunate circumstance. Some students tend to look at one or the other of these two examples that I just showed you and pick their favorite and throw the other one away. And that's you can't do that. So some students just have to think about vector fields as representing forces. They're like, I get gravity, I'm okay with electric fields, so to me, I'm going to think of vector fields, and look at it's just examples, right? So who really cares? I'm just going to always think of mine as representing forces. Other students might say, I don't really get that whole thing with gravitational fields. To me, gravity is just how much does something weigh, right? But I totally get, the idea of thinking of a vector field as representing fluids. And say, phooey on forces, I'm going to always think of vector fields as representing fluids. So I need to point out that neither of those is an acceptable choice. There are going to be things that we're going to do with vector fields, some that require interpreting the vector field from the point of view of forces. Certain applications insist on this, and thinking of it as a fluid will not make any sense at all. Okay, so you got to get on board with the idea of thinking of vector fields from the point of view of forces. And there are other things that we're going to do that require thinking of the vector field in the from the point of view of fluids. And if you insist on thinking of vector fields from the point of view of forces, it's not going to work. It just doesn't make any sense, right? So you have to be comfortable with both of these, thinking of vector fields as representing forces, thinking of them as representing fluids. Both of these are going to be a big deal. So make sure that you digest both of these previous examples that we talked about, and before we go on to applications. Okay. All right. So yeah, both are critical to the course. Okay. Yeah. Okay, so now the book makes some choices here in section 15.1 that I'm not really personally care for myself. It's fine, I suppose, but I wish they hadn't. That being said, they did. We are using this book as our textbook. There are questions that you're going to have to answer in this section 15.1 that, I kind of wish you didn't have to deal with right now. To me, it would make sense for you to deal with those at a later date. So, anyway, in order to be consistent with the book, I'm going to talk about some things that I don't think we're really quite ready to talk about. So I'm going to give you some apologies as we go through this next couple of pages. The apology is going to be in the form of, I can't really give you a good reason for this just yet, but here's the formula. And I hate doing that. It's mathematicians don't want to. We're very uncomfortable with this kind of thing. But anyway, here we are. So we'll justify all this stuff later. I'll give you a context and a point of view on all this stuff over the next several weeks. The book just wants to introduce these objects now out of context, in my opinion. So here we are. Let's talk about vector fields in R2. So keep in mind a vector field in R2 looks like that. Right, so given any input point in X2, there's an associated field vector in R2. Okay. To that vector field. By the way, a notational point. Very common to take the field vector, look at its individual components. Keep in mind those individual components are functions. It's very common to call the first one P. It's very common to call the second one Q. Doesn't really matter. It's an arbitrary choice, but it's pretty common. So I'm going to get on board with this again as a very common choice of notation. So it's arbitrary, but it's also harmless. And again, you're going to see this a lot. So P and Q. P means the first component of the vector field. Q means the second component. And with that having been set, here is this thing called Green's operator. It's dq dx minus dp dy. Those are, of course, partial derivatives. That's a formula. And it is extremely natural, geometrically. There's a nice point of view on this, physically. And I'm not going to tell you what those are right now, because I would have to do so completely out of context, without any justification. It would seem totally out of, just like, out of thin air. And I don't want to do that. Right. So anyway, that said, you do need to know that this is what Green's operator is. This is the formula for it, and we will make sense out of it in what I think is a reasonable context later, where I think it makes more sense. Okay, here's another formula that you need to know about. It's called the divergence of the vector field, and the divergence is sometimes represented with this notation and is computed by that formula. dp dx plus dq dy. It doesn't look terribly different, but it's a very different thing. It has a very different geometric interpretation, a very different physical interpretation and applications. None of which are we prepared to give any reasonable motivation for at this point. So rather than just make some bold assertion of what this means and ask you to take something on faith, not a habit that I want to encourage in y'all, right? Let me just say this is a formula, and you need to be able to compute with it for some homework problems. And I will give you a really good way to think about this geometrically, with I think a very plausible mathematical justification, and some great applications of this to physics and engineering. when we have the appropriate tools. And again, right now, we just don't. Okay, I'm going to quit apologizing. It's the same apology over and over again. Here are some other things. If we move now on to R3, by the way, again with the notational convention, the component functions very commonly are called PQR. Sometimes they're called F1, F2, F3 also, right? But I'm going to stick with PQR just, again, it's a very common choice, yes.
So like the above formula would just give like some real value?
The what now?
Like the above formula?
Yeah. Both of these above formulas, this is a real valued expression. Yeah, that's right. And this is a real valued expression. Yeah, there's no commas in there. It's just, there's a single formula, and it's a real valued thing. Okay, so for fields in R3, there is this thing called the curl of a vector field, denoted by this and computed with this formula. Now, by contrast, that is not a real value. This is a vector. You'll notice there are 3 different components there. 1, 2, 3 components to the curl of a vector field. So now, what does that mean? Why do we need to represent it with a vector? How do I interpret that geometrically? What does this have to do with physics or engineering? We're going to make great sense out of that later on. We just can't right now. Okay, I said I would quit apologizing anyway. Sorry. And then likewise, something called the divergence. It's you might notice the similarity there with notations. And here's the formula. You might even notice the similarity in the formulas. This looks just like the first 2 terms of that. So the 3-dimensional divergence just has sort of one extra term. Kind of plausible looking, I suppose, algebraically. Anyway, we will talk about this and make more sense out of it later. So, heads up, these are certain constructions that you'll need to do some computations with. I do want to introduce a notation that's very common. Divergence is sometimes written as del dot F. So remember this thing here called del. We've previously written gradient like this. And the idea there is that gradient, which is partial with respect to x of f, partial with respect to y of f, partial with respect to z of f. Notice, I can think of that as this operator, del, applied to f. Well, you can kind of think of it that way, I suppose. Just kind of notationally, kind of suggestive of that. So, in some sense, if you will, pulling out this operator, this what I've got circled in the yellow, pulling that out of our notation for gradient, thinking of it as an operator on its own. As it turns out, not terribly surprising, I suppose. But if you were to take that and kind of dot it with f, keep in mind that f. Here, let me write this down here. If we were to think of a vector field F as, P, Q, R, this dot product would say kind of pair them up and add them up in that way, and notice you get exactly the formula for divergence. Now this is we're abusing notations here a little bit, so let's just go ahead and be forgiving of the notational abuses there. But nevertheless, that's a pretty reasonable way to think about divergence, and it turns out it's a very handy, very natural notation. So we are going to use this notation. It's very, very standard, by the way. And I'll, again, just from my own personal experience, as a second major in physics as an undergrad, I saw this notation, del dot F, to represent divergence, probably more than I saw this notation of div. So del dot, gotta get on board with it. You gotta get used to seeing that. You're gonna see that. It's also slightly fewer pencil strokes. So it's a little bit of a time saver, a little bit of an ink saver, a little bit of a paper saver, so everybody wins. Okay. Analogously, you can think of curl as a kind of a cross product. And it's this is an exercise everyone should work out. But notice this formula we have here for curl kind of doesn't that structurally look kind of like a cross product? Cross products are computed as a bunch of little 2x2 determinants. And those look like 2x2 determinants. And if you were to just write down, along the lines of this sort of notational abuse, if you were to write down a reasonable guess of what should this thing here mean, del cross F, you get the exact same formula as that curl, as it turns out. Weird. Again, very natural, as we'll see later. Okay, so heads up on these notations. You're going to see them. Okay, very, very quickly, and I say this just so you go kind of understand the context of some of the exercises that you'll see in 15.1. It turns out that it makes sense to compose some of these operators in certain ways, and how this makes sense, I really can't justify right now. It's going to make sense later on. This is kind of a big deal. It's going to take pretty much all of chapter 15 for me to really flesh out, why all of this makes sense. But anyway, so here's what's going to be coming. In R2, it's going to make sense to think of gradient as a function that takes in real valued functions and gives you vector fields, and then to think of those vector fields as things that you might naturally want to take Green's operator of, resulting in then real valued functions. So composing Green's operator and the gradient operator like this, right? Doing Green of gradient. It's going to turn out this is a really cool thing to do. This is really natural in certain ways. Again, sounds context, but be on the lookout for this. We're going to kind of see an example of this, pretty soon. But anyway, be on the lookout. Likewise, in R3, it's going to make sense later on, but be on the lookout for this. It's going to make sense to take curls of gradients. That ends up being a natural thing to do. And likewise, to take divergence of curls. It's going to turn out to make a lot of sense. Again, just heads up, this is just a little bit of a sort of foreshadowing. One nice thing about it is each one of these is something called an exact sequence. I'm not going to be able to justify that in this course, but roughly speaking, what that means is that everything has a lifetime of 2 in some sense. So, for example, if you take a vector field, if you take a real valued function in R2, if you compute the gradient of that to get an ensuing vector field, if you then compute Green's operator of that gradient, you will get 0. And I'm thinking of 0 as being death in this little metaphor of mine. Right? So, it has in some sense, a lifetime of 2. It lived through the gradient and then it died with Green's operator, so lifetime of 2. This is further, it is further the case that if you have some vector field, if you were to take Green's operator of it, and if you were to get 0, everything dies after 2 steps. So let's ask an associated question. This vector field for which Green's operator is 0, is there some real valued function whose gradient is that vector field? Well, everything dies after 2 steps. Everything has a lifetime of 2. So yeah, it has to be. There has to be an associated function whose gradient is that original vector field, because when it dies by way of at the hand of Green's operator, that needs to have represented a lifetime of 2. So anyway, now why these statements are true, we're not even remotely close to being able to talk about yet. But anyway, this is a partial justification of why these compositions are really interesting to look at, really natural in a lot of ways. So just a little bit of a heads up there. Okay, I am, by the way, I have to say this, asterisk. I'm ignoring. There are some very important regularity requirements. We have to make sure that these vector fields are defined on the entirety of Rn, and there can't be any discontinuities. There can't be any. Everything in sight has to be appropriately differentiable, and these kinds of regularity conditions are very, very important. And we just can't go into that in Math 212. It's not really what this class is about. This is just, let me just say, with that asterisk, making certain big assumptions that we're not going to delve into very much. Okay. So there's various patterns that I want y'all to be on the lookout for. I'm going to be pointing out as we go through chapter 15. I think these are really big deal. Heads up as we go through the rest of chapter 15. Okay. Yeah. So we're going to go back to computing more kinds of integrals. Let me remind you what we've done so far. Here are the integrals that we've talked about so far. We've talked about single variable integrals, Calc 1, ancient history. Y'all remember single variable. Then we talked about double integrals. Now, double integrals are a fundamentally different kind of a Riemann sum, fundamentally different construction. Triple integrals, totally different construction. That's 3 separate kinds of integrals. They're all kind of chop it up, add it up, right? It's all, in all cases, you have these domains that you chop into little pieces, and on each little piece, something is going to be some density times size. There's always a real simple problem on each little piece that you then add up over the entire domain. So chop it up, add it up is the unifying, broad stroke feature of these 3 kinds of integrals that we've talked about. And then we introduced a fourth one a couple lectures ago. Surface integrals, right? So if you have a surface, a 2-dimensional surface in space, right? And you want to do a chop it up, add it up on that surface. Well, we're in space. So this is not a double integral exactly. But it's not a triple integral either, because a triple integral, the associated size is volume, and we're talking about a surface. It doesn't have volume. It has area. Right? So fundamentally different construction. We had to define a new kind of an integral that we called a surface integral. Well, here we are with integral number 5, called a line integral. I'm going to further refine that and say a line integral with respect to arc length. You'll see why I need to include this little clause here later on. So mostly that's we're going to call back to that in a little while. But let's just, for the moment, line integral. So again, we kind of vaguely referred to the notion. I mean, suppose you have some curve in space, and again, suppose you want to do a chop it up, add it up. Suppose this is a bent wire with a non-constant density. So mass per unit length varies across the wire in some way. Now, how would you compute the total mass? Well, chop it up, add it up. But this isn't a double integral because we're not talking about areas. And it's not a Calc 1 single variable integral because the domain itself is sitting in 2 dimensions. And we made a vague reference as a kind of a motivating example for talking about surface integrals that I can view this page here is really kind of review. I can view that as the image of an interval by way of some function. Hey, that's a parameterization. I made that observation. I can look at a little piece of this curve, itty-bitty little piece of that curve, and ask how does that little piece of the curve as an image relate to this little piece of the domain as a pullback, right? So what's the relationship between that size and that size? How much does this function stretch size? What's the stretching factor? Remember we made the observation that, well, that green piece of curve is relatable to this blue dx vector, our position differential, right? Dx. I can understand ds with dx. I can understand the dx vector by its components its components are, well, the scalar dx and the scalar dy, and how do the coordinates x and y change as a function of t. Now, that's single variable calculus, and we wrote down formulas, and our punchline was that the dx vector is v dt, and the ds scalar, phi being its magnitude, is then magnitude, of the velocity. So that, speed times dt. Okay, and that gives us what we need to know in order to do the pullback. Right, so ds is v dt. Notice that means that this thing here, our stretching factor, the thing that we multiply by dt to get ds, is the speed. And everything else is just a matter of sort of plugging in, sort of just a plain old pullback. Right? So it's morally, strategically, this construction is just like change of variables. It's just like surface integrals. There's an output size, there's an input size. The green output size relates to the yellow input size by way of a stretching factor. There's the formula for the stretching factor. Plug and chug at this point. Okay. All right. So quick examples. Suppose you have some rod in space, bent wire, like that. Right. Suppose you have density, on that wire. So mass is distributed across that bent wire according to a certain formula. There it is. Density is a function of position. Right. So we've got our parametrized curve. We've got our density formula, and let's suppose I want to compute some stuff. Maybe I want to compute the mass. How do I compute the mass of this bent wire? Well, mass, chop it up, add it up. Right? It's density times ds. So mass is unavoidably this brand new kind of integral. It's this line integral that we just defined, which we wrote down formulas for. Okay. ds is v dt, as discussed on the previous page. Now, what is this v thing? Okay, well, yeah. So we're gonna have to go through and deal with the finding the stretching factor. Don't forget our formula for stretching factor right here. It's speed. Right, so there is a calculation to be done there. So you got to compute the velocity. You got to take the magnitude of that velocity to get the speed. And details for this particular example give that the stretching factor, the speed is this formula here. And 2 seconds. Our ds then is speed times dt, and so our integral simplifies like that. Yeah, you had a question.
My question was just to make sure it was velocity, not like just like a random variable.
Yeah. So the stretching factor is always the speed. It's always the magnitude of the velocity vector, and don't forget the velocity vector is just the derivative of the parameterization. Yep. Always that. Yeah. Which is a nice thing, right? That this construction, whenever you're describing a curve by a parameterization. Yeah, the speed is always the stretching factor. Very, very convenient universal fact. Yeah. Okay. All right. So everything else is kind of plug and chug. Let's see here, real quick. What do you do with this x thing? Well, so density is x plus y. What do you do with the x? Well, okay. Don't forget that x is t. Don't forget that y is t squared. And now notice what we have here, what we've ended up with. That's a plain old Math 111L single variable integral, and plug and chug. Likewise for all the rest of the examples on this page, they're all just rewrite the question at hand as a line integral and plug into the given formulas for how to compute line integrals. Okay, we'll call it a day there. Sorry to go a little over. See you later. Have a good day. Oh, don't forget to turn in your homework if you haven't already. And if you came in after I checked attendance, make sure I get your name. Okay.